Welcome everybody to Tasking's three-part webinar series. My name is Florian Süßmeier and I'm a product marketing manager at Tasking. And today I will be the moderator of the webinar. In today's first part of the webinar series, how to develop an AUTOSAR compliant AURIX application, part one, the tasking toolchain. Our field application engineer, Roger Smith, will guide you through the main features of the tasking tri-core VX toolset and show you how you can overcome the challenges of developing a multi-core safety application using different AURIX variants with multiple AURIX cores. Then he will also briefly introduce the process of optimizing and load balancing the embedded software running in a multi-core AURIX safety application using the tasking suite of performance tools. And he will give a brief overview of the tasking safety products designed to ease the qualification of your ISO 26262 application. Then please move to the next slide. Thank you. We are active partners with leading OEMs and tier ones, and our focus is safety critical software development on multi-core architectures. Tasking provides a complete development environment that allows software engineers to develop reliable, safe, and high performance applications. We are also active in regards to the software development V-cycle and provide tools that can be used in different stages, as you can see here on the slide on the right side. For software development, for example, we are offering the Tasking VX toolset consisting of a compiler, linker, locator, and simulation debugger. All of them developed according to ASPICE Level 2 and TÜV certified according to ISO 26262 up to ASIL D. In addition, with the latest qualification kit, Tasking is now also supporting the IEC 61508 up to SIL 4 for industrial applications. Supplementary, Tasking is offering LAPAC performance libraries and qualified C math libraries as per ISO 26262. And the Tasking embedded profiler and the multi-core performance tool support part of the integration testing. In addition, you can see here also we are offering a static analysis tool, the Tasking Safety Checker, to ensure freedom from interference. And for hardware configuration, the Tasking Pin Mapper completes our portfolio. This webinar will be recorded and it will be available on our website. In addition, we will send you after the webinar a follow-up email with the link where you can access the recording of the webinars. In case there are any questions during the webinar, please ask at the end of the session. We will then have a question and answer session and try to answer all of your questions at the end. Let me introduce the speaker of today's webinar. Roger Smith is our field application engineer within Tasking. He has gained a lot of experience with over the last 25 years implementing and debugging automotive electronics. In the past 12 years of his career, he spent as an application engineer supporting braking, EPS, passive safety, and ADAS applications for a global leader in the automotive semiconductors. And currently, Roger, as I mentioned already, is a Tasking field application engineer supporting a wide range of multi-core embedded software development tools for the North American region. Roger has a BSEE from Michigan State University and an MSEE from Wayne State University. So then I will hand over to Roger and he will continue with the presentation.
Thank you, Florian, for the kind introduction. I'd like to wish our attendees a good morning, good afternoon, or good evening, depending on what part of the world you're joining in from. In today's webinar, we will focus on part one of a three-part series on how to develop an AUTOSAR compliant ECU with an AURIX microcontroller. We will be focusing today on the OEM system requirements and how they relate to the different aspects of an ECU design, specifically the hardware, software, safety, and performance. The webinar will detail how the tasking toolchain effectively and efficiently addresses these requirements to help ease the daunting task of designing an automotive safety application. Please stay tuned to the end of the webinar, where I will provide some details on parts 2 and 3 of this exciting look into the embedded development activities of an automotive Tier 1 ECU design house. As we can see by this picture here, basically all applications on today's automobile have some type of ASIL or safety requirement. Clearly, applications like anti-lock braking and electrical power steering all have very high safety ratings of ASIL D, as it's very important that we not injure our drivers by losing braking or applying inadvertent steering torque, to the automobile. But you can also see applications like automotive lighting, and even with some body constraints now with seat heating and other interior occupant applications, you have some ASIL rating associated with them. These advances in the automotive market tend to point that automotive drive, ADAS, cybersecurity, and the braking and steering system systems has led the terms of automotive and safety being synonymous with one another. In the upcoming discussion, an OEM will approach a Tier 1 ECU supplier with a safety-related use case. That Tier 1 will face many questions during the development of the embedded safety application. By the end of part 1 of the webinar, we hope that the viewer will realize that tasking is your one-stop shop for AURIX development. We see here a top-level view of the OEM's block diagram here of an ECU system. You can see the many different aspects of that system. We have a microcontroller here in the middle. Typically, you have a safety ASIC, which supplies some power supply, fail-safe, watchdog, in some cases, even redundant A to D converters. You'll see there's a plethora of sensors that are used here, either for doing motor position, motor commutation, picking up driver intent, vehicle dynamics, etc. You can see we have a bridge driver over here with the MOSFETs, which are used for controlling the actual motor. And then you can see here with an autonomous type or AD type vehicle, we're using some gigabit Ethernet here to communicate with the sensor fusion module and the basic camera, radar, LiDAR, or other ADAS sensors like ultrasonics and HAD mapping. We will focus primarily on the AURIX and the software implementation of this block diagram in today's webinar. So we will definitely highlight the multi-core microcontroller that's needed here to isolate the different ASIL-rated software blocks in the application. We will also be focusing on the redundant sensors for the system control. Obviously, as you're driving down the road, you cannot have one sensor fail and then lead to a catastrophic event with the vehicle. And so in these instances, many different OEMs require multiple sensors performing the same function, maybe with a little bit of hardware diversity. And they also require some software diversity in terms of which peripherals of the microcontroller are used to measure or interpret those sensors. And we'll be talking a little bit more about that. And we'll also be highlighting software over the air capability and making sure that the system can meet the different cybersecurity requirements that are dictated by the OEM. Moving on and looking at the hardware requirements that were posted or that were provided by the OEM to the Tier 1. The first requirement is that the OEM requires that the tier 1 only use 2 of the available 3 cores of the AURIX 29 series microcontroller. They're specifying only using 2 because the third core is being reserved for the OEM. In today's environment, with a lot of the liability and questions revolving who's responsible for autonomous cars, a lot of the OEMs are implementing the A to D functionality themselves. And so in this particular use case here, they are also requiring that the third core be reserved for their use. In addition, the OEM is requiring that the hardware use a dual lane architecture approach. In the previous slide here, I showed a top level block diagram of a standard EPU or EPS type system. If you look at a dual lane architecture, basically take that exact same picture and put it put it next to the other core, and then that's what a dual lane architecture would mean. So you basically have a copy, 2 copies of the same system next to one another. In the event, say the safety ASIC fails, in one of the 2 block diagrams, you have the safety ASIC in the other block diagram to ensure that you still have steering torque. We are also they are also requiring that we remain fail operational. So if we do have a fault in our system, we must still work. We can't just execute or implement a reset. As I previously stated, they're requiring that we provide multiple sensors to support a 2 out of 3 strategy. And they are also requiring that we implement some hardware or software diversity where feasible. With that, the motor drive, sensor IO, and safety checks must use multiple diverse AURIX peripherals. And I will highlight those details a little bit more on the next slide. One of the next things that the OEM is requiring is that a motor control demonstration be provided as soon as possible. This will allow the OEM to determine the tier 1's approach to running the motor. That this hardware does not need to be production intent, so the OEM realizes that development is still ongoing, but it must utilize the production intent microcontroller. And with that, the code size and execution times included in those requirements help to outline the overhead requirements for possible late design cycle feature additions and post-production OEM updates. And last but not least, the CU design must support multiple vehicle platforms. As you can probably imagine, a nice steer evasive system on a high-end luxury vehicle, as when it's introduced to the market, will, if it works well and if it's safe and if it provides all those features that are needed in the market is going to demand that be distributed on other platforms within the vehicle hierarchy. And so it must be possible also that we're able to scale to those different vehicles. So for example, if we have a high-end Lincoln, for example, that has the system, and now we want to use it on a lower-end based Ford vehicle, which is a lower cost vehicle, you must be able to utilize a lower cost AURIX microcontroller to do that implementation. And so the design must support this scalable approach. So let's look a little bit more into detail into our lead microcontroller. So as I previously stated, we'll be using the TC29. You can see here that within this microcontroller, we have 3 performance cores. Each one of these performance cores has its own program and data memory. You can also see here that I've highlighted over here a number of the different peripherals that are supported on this microcontroller. You can see here that I have 3 different timer modules. I have a capture and compare, a general purpose timer, and the generic timer module. This is where we can provide some diversity in how we do our motor control algorithms. You can see here I provide I show the 2 different A to D converters. We have both a differential and a single-ended A to D converter. And again, when doing plausibility checks on our sensor data, In the event there's an issue with one of the ADC converters, the OEM is requiring that we use a second technology independent or a separate implementation of the ADC to do the check. And then at the bottom here, you can see I've listed a number of different communication interfaces that are supported by the AURIX, be it Ethernet, FlexRay, UART or LIN, and then your basic CAN. So in this particular application, we will focus heavily on the 3 tri-core performance cores. We will look at the different timer peripherals for motor control and sensor I/O, and then we will look at the different diverse ADCs for fail-safe checking, plausibility comparisons, and sensor I/O. It is important going forward that we realize that the dynamic evolution of autonomous drive and steer-by-wire type applications and strategies leads to many different upgrades in the embedded software. Some of these developments can take place very late in the design cycle or even after the vehicle is in production. I mentioned earlier about taking advantage of the software over-the-air update requirements. And the reason why we do this is because we can implement these new features while the vehicle's already out in the field. We don't have to therefore bring the vehicle back into the shop and have a high-end cost associated with that all those vehicles coming into the service bay. So let's look at some of the common hardware challenges now that our Tier 1 is facing. First of all is, how do they ensure that the PCB will support multiple AURIX family members? When you lay out a PCB, a printed circuit board for an electronic control unit, there's a lot of validation that's associated with that. And it can cost a significant amount of money in order to ensure that that PCB meets all of the different requirements that the OEM will place on it. And so if we've already highlighted the fact that with a scalable application that we need to take advantage of a scalable microcontroller, how do we use one PCB, say, to take advantage of a TC23 or a TC27 or a TC29? So this is a common problem that our Tier 1s encounter. Another, as you can see also in the requirements, the OEM is requested a demo. So they want to see something working. They want to see not production intent hardware, but they want to see some hardware and they want to see it running quickly. So how do we get software up and running as quickly as possible? So what we'll see is that one of the tasking tools does provide the C code for the AURIX microcontroller. And last but not least, how do we seamlessly move the AURIX port mapping? So we lay out the microcontroller, but now we still have to do all the other circuit layout for our ECU. We have to still lay out the bridge driver. We have to still lay out the safety ASIC. We have to still lay out our MOSFETs and our sensors. How do we take advantage of how does the AURIX, after the AURIX has been laid out and designed, how do we easily incorporate that into our PCB design or our schematic capture? And how we do this is via the tasking pin mapper tool. So this is a tool that comes with our tool set. It is also available as a standalone product. And what the tasking pin mapper does is it easily allows you to configure AURIX first and second generation devices to meet the different peripheral and I/O requirements of the application. The current version of the tasking toolset, version 6.3R1, supports the following AURIX 1G and 2G variants. And you can see here that the whole family is supported here of the AURIX first generation and second generation. And in many instances, we have upwards of 5 different package types that are supported per family member. The next highlight of the AURIX pin mapper tool is that it does allow you to automatically generate that basic initialization code. So it allows you to set up data direction. Are you using a port IO as an input or an output? Is it a pull up? Is it use open drain? Is it in a push-pull configuration? What are the thresholds? Are we using CMOS or TTL? And more importantly, is this speed grade? So a lot of people who are first using the AURIX don't realize that there's multiple levels of speed grade that are associated with the different pins of the AURIX. So for example, if you need to drive a high-speed bus, for example, there's the highest speed grade pin has got the additional current capability in order to drive the capacitive loading on the bus so that you don't get rounded edges. If you don't know this up front, you may actually select a pad or a pin that does not have the necessary speed grade necessary for driving a square wave on a highly capacitive bus, and then you can get rounded air edges on your signals, which can lead to faults. And so within the pin mapper tool, we allow you to, we highlight that for you to help you overcome some of those difficulties or complexities associated with the AURIX. The AURIX, or I'm sorry, the pin mapper automatically generates data files that work with the PCB design tool provided by Altium Designer. And as previously mentioned, a standalone pin mapper tool is available. What I'm showing now is kind of a screenshot for the pin mapping tool. And what you'll see is information is shown in two different ways. First of all, we have a graphical view, and this is all of the different pins on a particular package. So our lead product or our production intent microcontroller was a TC29. We are using the 292 ball BGA variant so that you can see visually where the ball placement is on the package. And this greatly aids in floor planning for laying out your PCB board. Over here on the left, we can see that you can view the different peripherals in a hierarchical peripheral view, or you can go through and you can manually select them based on their port name. So I'm showing the hierarchical view here. And where you can see the advantage here is, say, for example, we're laying out CAN. And so we're laying out CAN has a receive and a transmit pin. You can see here that we're using 20.7 right here for our receive pin. Now, if you look at our transmit pin, you'll see that we have multiple different options. We have 8 or 9 different options here based on the multiplexing strategy of the AURIX of where the transmit pin of that CAN node can be placed. You can see we can place it over here at 2.0. We can put it way over here. But now when you're laying out the circuit board, you can see very easily that that makes no sense that we have our transmit on this side of the package and we have our receive on this side of the package. So at least it allows you to see that, you know, you can pick an option that aids your circuit layout. And this is very helpful for things like Ethernet or SPI. Where you have 5, 6, 7, 8, 9, up to 15 different pins that are associated, and you want to cluster the pins in close proximity on the microcontroller for ease of layout. The other thing that you'll notice is when everything is entered incorrectly and there's no conflicts, that everything will be green. And once all of your pins are labeled green, at this point you can automatically generate your code. If you do have an error where, say, you've double used you've used CAN 0 node 0 twice, where you specified both 2.5 as an output and 33.8 as an output, then you're going to get an error here and you won't be able to automatically generate your code until you resolve that issue. So the pin mapper tool is a very popular tool. It's used, we have a lot of requests for people just to use the pin mapper tool. So moving on, so we've addressed kind of our hardware requirements. Let's look at our software requirements. So the OEM is specifying that our software must be AUTOSAR compliant, and they are specifying that it be AUTOSAR version 4.2. They're also requiring that we use the BSW stack provided by Vector. And more importantly, remember we talked about this dual lane architecture type implementation. So there'll be 2 different microcontrollers in our system. We have our tri-core or our TC29 to support the classical AUTOSAR type requirements. And then also there's going to be, since this is in an ADAS type environment, we are going to try to take advantage of the adaptive AUTOSAR as well. And so we will be using an ARM based microcontroller POSIC ARM for that leg of our design. And last but not least, you know, the OEM is very adamant that we must support both C and C++ in our implementation. So the increasing complexity of automotive embedded electronics, you know, it results in a huge amount of data collection and real-time processing. And so a big hurdle in the software development process is how to integrate these different modules, be it engine control, infotainment clusters, from different vendors without having compatibility issues. And so as we keep this kind of in the back of our mind, let's take a step back here first and look at some of the software implementation basics. The first thing is that in our system, we're going to need an operating system. We're going to need a BSW, some complex drivers. We know we're going to need MCAL. We're going to need some application software. In many cases, we use some MATLAB, Simulink type models. So there's lots of pieces here that have to work together. And so your tool set has to work together and support each one of these pieces in your overall design or implementation. So there's two approaches that are out there. You have either the AUTOSAR approach or you have the approach of writing code for each ECU separately. For those older audience members, you probably remember the little later, where, you know, code is written specifically for a particular ECU. And then, you know, if a change comes later on down the road, you know, it's a very time and resource burdensome to rewrite, you know, everything for the new requirements or the new microcontroller that's been selected. The younger aged guys in the crowd who are familiar with the AUTOSAR and the MCAL or the AUTOSAR type implementation, they realize that this abstract software implementation to kind of create the standardized interface between software and hardware is required in today's automotive environment. And so knowledge of this is required to move forward. So AUTOSAR developed software is basically, for the newcomers out there, is easier to share between vehicle systems. Communication stacks help to facilitate communication both inside the ECU and between other ECUs. There's middleware features that are also included that support things like memory services, diagnostics, and safety. And if we take a quick snapshot here of the classic versus adaptive AUTOSAR architecture, the main point here is that adaptive AUTOSAR is not replacing classic AUTOSAR. They basically coexist in the same automotive ecosystem. So each have their strengths depending on the application. So for example, the AUTOSAR Classic offers a high level of safety criticality. It's got lower computing power, you know, around 1,000 DMIPS, but it's very fast. And then when you look at kind of the adaptive AUTOSAR, it's very dynamic, it's very updatable, supports cloud-based processing, supports IoT. It's middle of the ground in terms of speed. ASIL B is typical, it could go up to ASIL D, but it's generally for very high computing power requirements. And so you can kind of look at your traditional braking or EPS type safety applications as being your AUTOSAR Classic, where you have, again, that high level of criticality, very precise, very fast. And then things like your cloud-based processing for HADMAP, say, for example, for high definition for doing trajectory planning around your vehicle, would be more of an adaptive AUTOSAR type application. So there's a lot going on in the software side of our project. And so what are some of the challenges that our tier one is going to face? One of the main challenges is that they're using AUTOSAR. So they're using an AUTOSAR compliant version of the tool set. And they have different sets of compiler options for the different pieces of their software. So Infineon will come and say, hey, for MCAL, you must use these compiler options. Vector then says, hey, but for our BSW, you need to use these compiler options. And then the tier one has their own application code, and they have their own types of requirements, based on whether they want to compile for speed or for code density or however they want to do it. But they only have one IDE. How do they support all of these different requirements? You also have the case where Vector and Infineon are providing different compiler options, like I mentioned, but you also have the case where, say, for your MCALs, only certain Infineon will only verify certain versions of their compiler to be MCAL compliant. What if you need to use a feature for your application that's in a different version of the tool set? How do you take something that's an MCAL compliant version of the compiler and say a legacy application version of the compiler set and put those two together? So these are many different challenges that the end user can face. And how does tasking help you solve those problems? So tasking tool sets basically provides guaranteed compatibility with all leading third-party solutions, including AUTOSAR operating systems, MCAL drivers, and debuggers. We offer flexibility with different optimization settings for MCAL, BSW, and application code. So cross-compiling, which is not supported by all different vendors that are out there. Cross-compiling as tasking supports it allows you to compile legacy code with newer tool set versions, and it allows you to take advantage, say, of some of the newer features that are in version 6.3, and still being able to utilize Infineon MCAL version 6.2 R2 with only one out file and using only one IDE. One of the other features of the tasking toolset is that it's a multi-core compiler with a versatile universal linker, and it supports all of the cores that are integrated in the AURIX. So the AURIX has the performance cores, as we've talked about. There's a generic timer module core. You have ARM-based core in the HSM module. You have an 8051 in the standby controller. And you actually have a PPU compiler as well. And our tool set supports all of these cores of both the AURIX 1G and 2G families. Again, not all of our competitors can do that. So that's another way where we differentiate ourselves from our competitors. The in-house, our compiler technology is all developed in-house. Safety is our focus, and there's no open source that is used in our compiler. We do support C and C++ for both our tri-core and ARM compilers, and we do offer static code analysis for MISRA and cert-C checking. And last but not least, our newest version of the compiler supports position-independent code and data modules, where they will work anywhere within the memory space. And this is very beneficial, again, for things like software over the air, where a new feature, say, that's developed late in a development cycle, or after a vehicle is already in production, and now we're trying to dump that into Flash via software over the air update. We don't have to worry about placing it in a very specific region within memory. We can, it's easier. We can kind of place it wherever we want, and it will still work. So I've provided a quick snapshot into the different editions of the tasking tool set. So you can see here that we can go for standard, professional, premium, or our enterprise bundle, and you can see that all of the different tools include our pin mapper. All of our editions include the tri-core compiler, and you can see down here for differentiation here that there's between the standard and the professional edition will allow the hardware debugger. In the HSM and the professional, and then you can see if we step up to the premium, we can then gain standby controller or peripheral control processor support. Secure Cert C secure coding is also available in the premium edition. And then you'll see down here below that we have a number of additional performance products that are available, and then we'll be talking about those shortly. So we've talked about hardware, we've talked about software. Let's talk a little bit about safety. So the OEM is requiring that our hardware and software be qualified for ASIL D. They're requiring that the compiler and tool development process be ASIL D certified by an independent third party. The C libraries must be qualifiable if necessary, and we have to look at compile, and there must have compiler options specified for certified ASIL D operation. And if these are not included in our safety manual, we must also be able to qualify them. Freedom from interference must be guaranteed for functions and variables of different ASIL levels. And then a key point here is that any compiler, assembler, or linker locator development issues deemed SIL 2, 3, or 4 present in the user source code must be understood and be able to be resolved in a timely manner. Interesting set of safety challenges, can be very complex and very arduous. There's a lot going on, right, for ASIL D software. And there's a lot of help that's provided, right? Infineon provides some certification that their MCALs are qualified. The Vector, for example, will provide some documentation that their BSWs are qualified. But we still have to make sure that our tools are qualified for ASIL D. We have to make sure that our compiler options are qualified. We have to make sure that every single time we compile our code, it's the same. We have to make sure that there's no compiler bugs, quote unquote, that have made it into our code, which can lead to a SIL 2, 3, or 4 event. So there's still a lot of work going on. Another big challenge is that time. Here, the tier 1 is stating, hey, time is being wasted because we're debugging MPU traps due to memory partitioning. With, again, this ASIL D application, you have ASIL B, C, D type different software components. You have some QM software components. How do you ensure that the ASIL A function is not trying to write a location in ASIL D? How do you ensure that a wild pointer from a lower ASIL level software block is not inadvertently accessing or trying to contaminate a variable from a higher ASIL related software component? Here, another requirement is I need to use two standard C library functions in my ASIL D code. Well, the standard C libraries are typically released as QM, but now it needs to be ASIL D. What do we do? So they need to have one of these math functions qualified for ASIL D. How do they proceed? And then the last point here is, hey, I want to use some special compiler optimization settings, but is this going to violate ASIL compliance? I can't fit my code in the microcontroller that my customer is telling me to use. So I need to turn on some optimization settings. By enabling those optimization settings, am I violating anything? Tasking provides a very safe portfolio, and we have many different solutions for ISO 26262. We do offer a certified compiler that's been certified by the TÜV Nord. So the tool set is suited for development for ASIL D software. We are ASPICE certified. So our tool set has been developed using a ASPICE capability level 2 compliant development process, which guarantees the highest software quality, basically ensures ASIL B code from the start, ASIL C under certain conditions. And we have certified development processes and quality assurance for all process and development steps. There is no third-party code in our compiler toolchain. Static code analysis is offered both with MISRA and CERT-C checks. We do have a safety checker tool, which does detect memory interference between software elements with different ASIL levels. I would really encourage you to tune into part 3 of our webinar series in April of this year, as Barath, my colleague, will be presenting many different exciting use case examples showing freedom from interference using our safety checker tool. Tasking offers a safety kit, which basically shows which has a safety manual, which shows all of the different compiler optimization settings for different ASIL levels. And we do have a inspector tool that's currently in beta testing right now, which significantly reduces the manual code inspection and provides enough information to perform a risk assessment and determining if you have any previous compiler issues that have high SIL related potential in your source code. So talking a little bit more about the inspector tool, benefits include, it inspects your complete project in one run and provides guidance if a patch is needed or not. It reduces time and the variability associated with manual checking. It's fairly easy to use with minimal integration effort, usable within the make file. And again, it warns if compiler output is impacted by SIL 2, 3, 4 issues, which are published on our issues portal. So if you're doing ASIL development, it's probably something to look into in the near future. Quickly, we're running up on the clock here a little bit. So our quality assurance provides issue traceability and qualifies the system to ASIL standards via performance testing suites and regression analysis. I did mention we are R2 certified with version 6.2 R2, and our safety manual does describe how to configure the tool chain for safety related projects, including recommended use cases, compiler options, and mitigation strategies for potential errors. Compiler library qualification per ISO 262 can be supported. And we are actually in the process now with a lead customer of qualifying CLibs. And so if you need qualified CLibs moving forward for your high safety, high level ASIL project, please contact us for more information. So now moving on to the fun part, we've talked about, again, hardware, software, safety, but what about performance? And so the OEM has also come up with a series of performance requirements. They're requiring that the 2 cores, which the tier 1 can use, core 0 and core 2, they must not exceed a maximum loading of 60%. The tier 1 must also guarantee that all tasks and timer interrupts are properly configured and meet system timing requirements. Basically meaning that we want to minimize the number of stalls due to cross-core memory access. And the OEM is requiring further autonomous drive type algorithms that they're going to need some LPAC functions to implement that. And so looking at some of the challenges, software over the air requires HSM, which uses an ARM controller. So do we need a separate compiler to do this? The software developed for the TC29X, but they also, the OEM has also told them that they need to be able to move to a 2.6. So how do they support the memory map of a 2.6, which is significantly smaller? And they, I have a soft release next week and core T0 is thermally shutting down and I have a large number of memory stalls. Can you help me? So tasking offers some optimization tools to help limit stalls and optimize the performance. And so we'll look at these briefly here, as again, we're running out of time. So our multi-core performance tool provides guidance to reach a safe and equally distributed system. Raw trace data can identify task switches. So it will go in and it will look at like if you're running an RTOS, for example, it will look at the number of tasks that are running, how many times they're run. It will look at, in a 3-core type system, it will say, it will look and it will measure, you know, the core loads of the different cores within the system. The embedded profiler is a tool that works kind of hand in hand with the multi-core performance tool. And it not only measures the duration of tasks, but it also helps to identify the exact location of performance bottlenecks and helps to resolve them. So it will identify data and instruction cache misses. It will identify stalls due to cross-core memory access. So if core 0, for instance, tries to access data which is in core 1, you know, since it has to go out over the SRI bus, there's the potential that it can lead to a stall. There is a new version of the embedded profiler which is coming out, and it will provide some additional AURIX device support. It will provide some flash programming support. It will also, one of the new exciting features is it will provide some DMA performance profiling. So it will help to look at the different DMA channels that you're using and profile them for performance as well. And last but not least, Tasking is the only supplier for the AURIX with an optimized LPAC implemented in C, which supports both the AURIX 1st and 2nd generation devices. And the LPAC, the linear algebra type functions help with the development of high performance signal processing in ADAS applications. So if we look at a high level overview of our tasking performance tools, you'll see here, I'm showing here a emulation device, Infineon AURIX. So this device has the emulation extension chip, which has emulation memory, the Aurora Gigabit, and the full MCDS type support interface. Basically, the AURIX communicates to the tasking performance tools, or the PC here, over the JTAG or DAP interface. So you take the ELF file, which is programmed into the ECU, the AURIX emulation memory basically goes to the tasking performance tools, and that leads to your multi-core performance tool and your embedded profiler. There are a lot of questions on this slide here. So emulation devices, if you've worked with the AURIX, are very expensive and they cost a lot of money. Production devices are, what are used for development, and the amount of memory that's available for emulation is dramatically different between an emulation device and a production device. So for example, an emulation device can have upwards of 1 meg to 2 meg of emulation memory. Whereas if you're looking at a production device like a TC27, you can have a buffer size of 6 to 8K. So you can, it's significantly smaller, and the impact of that is as this smaller memory fills up and it has to dump data to the tasking performance tools, and then be filled up again and move it back. And then, that's a very iterative process that if you're trying to use, both devices will work. Let me clarify that after the bat. So you can use either an emulation device or a production device with our tools. The problem comes into, I would say, the obtrusive behavior or intrusive behavior on the real-time application. So if you're trying to use a production device with a very small buffer and you're trying to trace an incredibly large amount of data that has to repeatedly dump the buffer, you are going to see some real-time performance impact there on your application. But the key message is that you don't need an emulation device in order to use our tools. You can use a standard production AURIX device just fine. Just to be aware of that caveat. So now our demo. So we've implemented a demo for our OEM. We've chosen here to use the Neutron Controls Rapid Engineering Development Kit, which is a really, really nice kit. Basically, you can see here in the middle, we have, these are variable pods. So you can have different multi-controllers here. So you can buy one for the 2.3, 2.7, 2.9, 3.3, whichever microcontroller you're working on. You plug in the board that you're using, and then all the other peripheral hardware stays the same. You have the ability to do hands-free probing of all of your signals here from your AURIX controller. And there also comes with a number of different boards. So you have a power supply board. Here you can see two BLDC motor drives with off-the-shelf BLDC motors. There's you have Ethernet, you have a ADAS camera. There's lots of different expansion boards that you can purchase. So in our particular application, remember the OEM has requested that we use a production intent microcontroller. So we have a 2.9X sitting here on our board, and they want to see some motor control. So what we're doing is we're using capture and compare initially the CCU peripherals to do our motor control. And what we're going to show in our demo is if a failure happens on one of our motors, that the other motor will kick on, so that we ensure that we have steering torque in the event of a motor failure. So if you can see here initially, we start with both motors running. So we're enabling redundant operation up here on our motor control. So you'll see at this point, after the system starts, we have one motor that is working. The other motor kind of is in standby. So we'll do some type of a failure, maybe a shorted phase or whatever on this motor, and then you'll see that the other motor will kick on and run. So we're able to, we were able to send this off to our OEM, and they understand our strategy, that we're able to work according to the requirement. So that brings us to our end here, to our conclusion. And so the tasking tool chain provides full support for all family members of the first and second generation AURIX. This allows full scalability. So it allows the end user to take advantage of potential cost savings by using a more cost-effective microcontroller where they need to. The tasking tool chain provides compilers for all the integrated cores. We get a lot of questions where there's different customers that are trying to use one particular microcontroller. We're trying to use, say they have the TC, the performance core, compiler, and they want to use an SCR, and they're like, hey, do you have a standalone SCR? And we're just like, no, we offer the whole package. If you just want to develop with the AURIX, use our tool chain. The tasking performance tools take advantage of the Infineon AURIX architecture knowledge to provide fast and efficient access to flow tracing information. So tasking and Infineon have worked together since the mid-'80s. And so there's a very close relationship there, and that's one of the key benefits that tasking can provide is insight into the AURIX architecture and knowledge into how the AURIX is developed and how it was created. And our performance tools take advantage of that know-how to provide efficient flow tracing information to you, the end user. Tasking significantly reduces the pain of qualifying software for safety critical applications. We offer the safety manual, our ASPICE compliant development process, our TÜV certification, our issues portal, our database, the inspector tool, safety checker, many different avenues for meeting your ISO 26262 requirements. And that basically wraps up our webinar for today. So thank you very much for your attention. I would like to invite you to participate in part 2 and 3 of the webinar series. Part 2 will focus on the performance and optimization aspects of the embedded system. So this will largely focus on the embedded profiler and the multi-core performance tool. And then I really encourage you to tune in mid-April for the for part 3, which will focus on our the safety aspects of the system and look at the safety checker freedom from interference tool.
Thank you, Roger, for your presentation. So as Roger mentioned already, please feel free to contact us anytime if you have any requests regarding a free trial license of any of our products. You can drop us an email to sales@tasking.com. Now it's time to answer your questions. You can use the chat function in Zoom or the F&A function. So we already have a few questions here, so I will read them out and then Roger will try to answer them. So first question here, some pins used for safety must not be neighbor of e.g. a VDD ball. Can one filter the list of available pins for a specific function, like ATOM1, channel 1 output, SPI1, based on this criteria? Or do you still have to log one by one and check it for yourself?
You can show the pins by different peripherals. I think, though, if you're talking about specific design rule type checks where you have to, you can't have like a say a pull, an active pull down pin being adjacent to a VCC pin, or like a sensor high pin that be adjacent to a ground pin. There's still, the tool does not perform that level of safety analysis for you automatically, but you can see, from the graphical view, you can see orientation. So you can show like ATOM, for example, next to whether there's an adjacent power or ground, but it will not do the static analysis or safety check for you. Hope that answers that question.
Okay, thank you very much. Are there any additional questions from your side? Anything else? Still have some time.
I would encourage anyone who's, sorry, Florian, anyone who's interested in a demo of any of our tools to contact sales@tasking.com. And we can, go through your particular use cases for your pin mapper tool. If you're having some problems and you need some help, by all means, please feel free to contact us. That's what we're here for.
Yes. There's another question popping up. The participant would like to know if the code generated from the pin configurator could replace the MCAL drivers related to DIO and port.
So I think, Florian, that's with our ARM XL release,
Yes.
Pin Mapper Pro, and do you have an update on?
Yeah, so basically our current pin mapper cannot support that, but we are planning to develop a Pin Mapper Pro version, which is on our roadmap. And here, then this will support the RMXL file output to use this then for the interface for AUTOSAR configuration tools. So this is currently under development, but this will be available. I cannot tell you when it will be available, but we are working on this one. So here's another question. If we are using low-level TC32XX, so the AURIX derivative, which it only has one core, based on your experience, what would be highest ASIL level that could be achieved?
Maybe can I answer this question? Is it possible?
Absolutely, Brad. Go ahead.
Yeah. Yep. So, I mean, in case you have a memory protection unit for your core, maybe you can achieve ASIL D, and this would basically depend on your design and from the hardware perspective, what level of ASIL can be achieved with your hardware. So if it is ASIL D, then with hardware, it's ASIL D, and depending on your software design, maybe you can achieve still ASIL D if you already have an MPU. That is if you want to have a mixture of different ASIL levels in your system.
Thank you, Bharat. Another question, are there any tools available to generate custom linker scripts?
Okay, so this was also in discussion. So we wanted to include this this custom generated linker scripts along with the safety checker. So this is still under discussion internally at tasking, and in case when we have some updates, we will get back to you.
Mhm. Another question. So here, are you going to show some details on a C++ use case? This is of interest not only for automotive, but for industrial and aerospace.
Well, we're always looking for ideas for new webinars, so we'll take that down as a suggestion. I don't think any of our upcoming webinars will address that topic.
Yes, but as Roger mentioned, this we are open here for any inputs, and if this is a topic of interest, then if you also have further questions about this topic, you always can contact us, and then our FAE can directly contact you and discuss. Another question. Accessing the DAP port can be done with MiniWiggler and then using USB connection to PC, question mark, or is some special hardware needed to connect PC to DAP port, e.g. something like Lauterbach?
That's absolutely correct. So yeah, so you can use the MiniWiggler. You can also use, you can use like IC5 5700 or Lauterbach, and then you can communicate through an API to get data that way. So there's multiple ways to do it. As I was showing in the block diagram there, yes, we were using a MiniWiggler.
All right, there's another question. Are your additional tools, safety and performance related, compatible only with applications based on AUTOSAR and MCAL?
So let me take this up. Basically, this is these tools work with the classical C programming, so embedded C programming. So AUTOSAR and MCAL is also one application of this. So to answer your question, in case you have classical software which is not AUTOSAR, then you can still use the safety checker and the embedded profiler and the multi-core performance tool.
Mm-hmm. Thank you. Any other questions from your side? So if you still have questions after the webinar, please feel free to contact us anytime. As mentioned before, you will receive a follow-up email after the webinar, including the link to the record of this webinar. It will be then uploaded to our website, and you can also have a look afterwards. So it seems there are no further questions at the moment. Then thank you very much for your participation of today's webinar. And as Roger mentioned already, there will be a part 2 focusing on performance optimization tools, which will be next month. And then there also will be a final part 3 on safety products, tasking safety products, which will then be held in April timeframe. So stay tuned and see you next time. Have a nice day. Thank you.
Bye.